Hello there, MCV4U folks. This is the lesson 6_4 on the properties of vectors. This today's stuff is going to be busted up into a little bit of pieces here. This video is the warm up, and there's a little activity, and I'm going to explain that in this video. Give you a little break, and you're going to actually do the activity. It should only take 10 minutes or so. Then I'll do the rest of the note, and when we get back to class, I think there'll be a clicker quiz, and then you'll have a chance to do homework, of course. This clicker quiz we might have done it last day, or maybe not. I don't know. There might be some clickers. Anyway, today's warm-up is a bit strange. It says if we've got the sum of two vectors, x plus y, and the answer is x, well, what do we know about vector y? Well, vector y has to be the zero vector, right? The zero vector has magnitude of the zero of y has to be 0, and the direction is any old direction. It's basically an undefined direction, the zero vector. And we call this idea, if x blah y equals x, then y is called the identity for the operation blah. And we know lots of identities. What are some other identity for other operations you know? Well, for multiplying real numbers, one is the identity, right? For instance, 7 times 1 equals 7. So for multiplying real numbers, there's your identity function. For real numbers, if we're adding or subtracting, what's the identity? Well, 0, right? Because any number plus 0 is any number. So there's that thing where we see the answer comes out. But these are easy ones, but it works for other things, like, for instance, functions, right? So what about things like function multiplication? If we had this and the answer is that, what would have to be true about g, the g function? Well, this thing is f at x times g at x, and then if that answer is f at x, we see g at x must be equal to 1. Well, that's a function, and we're talking about an operation on functions. So for function multiplication, g at x equals 1 is the identity. And the identity for vector addition is the zero vector. But what about for scalar multiplication? Scalar multiplication for vectors. Well, we remember that a scalar multiple of a vector is just a times that vector. But if we had the operation here, heart, blah, we got something blah u, and that answer is u. Well, what's this scalar has to be, right? The scalar equals 1. So scalar multiplication, the identity is 1. And for almost every operation, there is an identity. For most, anyway. This is the sort of thing that we're talking about today, which is these ideas of what can we do in general to vectors. So for instance, if we had two numbers and we're multiplying them, does it matter if we switch the order? Well, no. But if we had two numbers and we're subtracting them, does the order matter? Yes, it does. So is vector addition or scalar multiplication, is it more like this or more like this? Well, this is what we're investigating today, and that's what this activity is about. So you should have a piece of paper. Hopefully I've remembered to give that to you. There it is. And I'm just going to explain basically what this is. So under scalar multiplication is scalar multiplication associative. So what it's saying is this expression the same as this expression? Well, I don't know because I don't know what A, B, and U are. So what we would do is we would pick some values. So we could say, okay, let A be -2. Let's say B is 1/3, and U, the vector U, is some vector. We don't care. Not the zero vector, because the zero vector isn't very interesting. Make this a vector. Okay, there's a vector U. Dandy. And so we're going to build this expression, the left side. So what would 1/3 of U look like? 1/3 of U would be this vector that's about 1/3 as long. And I'm just eyeballing this. I could get out my ruler, I suppose, but I'm just going to eyeball it. Put my arrow on the end. And this vector here, that's 1/3 U. So this is 1/3 of U. And then if I have this vector now, which is -2 times 1/3 of U, so -2 means twice as long in the opposite direction. What I would do is I'd copy that vector, and you just measure it, right? I'm pressing Control and Enter. And then I'm going to switch the direction and make it twice as long. Well, let me make it twice as long. And then I'm going to draw another vector that's like that. Okay, great. So let me get rid of these other ones. So this is a vector that's this vector here. I'll make it blue so I'll do my other one in red. So this vector then is -2 times this vector I constructed earlier. So that was the vector that was 1/3 of U. This is the vector that's -2 times 1/3 of U. So the question is this the same as the expression that's on the right-hand side? Well, the right-hand side is, can I multiply the vectors first? And of course, I picked kind of stupid versions because now I'm going to have to find a vector that's -2/3 times as long as that, but that's okay. If you pick nicer values, you would have had a better time of it. But -2/3 of U. Okay, well, let me get a copy of this, and I want a vector that's in the opposite direction, that's about 2/3 as long. About 2/3 as long. Delete that other one. Well, that looked like it, right? 2/3 as long in the opposite direction. And so that's that vector. The question is, are these two vectors equal? And it's easy for me to do on the smartboard, but they are, right? They're exactly the same vector. So that means I've illustrated this geometrically. Why did I pick these values? For funsies. I just picked them for funsies. And you do a similar thing with these other ones to convince yourself that these properties are true. So because it didn't matter whether I multiplied it in the brackets and then took a scalar multiple of that vector, or I just multiplied the scalars first, I could do that. So this is the same as this. However, I see that fits. It doesn't matter. Okay? And now you're going to stop this video, and then you're going to do this. You're going to do this thing and then come back to the note.